Assalamu alaikum. It's Ahlam Deeb, and I'll be explaining Chapter 3, Kinetic Factors, Part 2. Before we start, please prepare your stuff. In today's video, we are going to learn how kinetic factors help in studying the kinetic of a slow reaction. Consider the oxidation reaction of iodide ions I- by peroxide sulfate ions S2O8 2-. It is a slow reaction that produces I2. Our objective is to determine the number of mole or the concentration of I2 produced during this reaction at different instants. When I talk about different instants, I have to prepare a chronometer. Also, I have to prepare a specific volume of each of the two reactants that have non-concentration. Iodine I2 has brown color and could be titrated by thiosulfate ions S2O3 2- in presence of starch. This is the color of iodine I2, brown color. This is a solution of starch. When I add iodine to starch or starch to iodine, a dark blue color is observed. To study the kinetic of our reaction, we have to prepare a magnetic stirrer with its bar and a large beaker in which I will pour the two reactants. But before, I have to prepare an ice water bath. In this ice water bath, I will put 4 Erlenmeyers that contain distilled water, the same amount of distilled water. This volume would be between 150 and 200 milliliters. This ice water bath will help me to block the reaction of production of I2 at the different instants. Now, this is the two reactants I- and S2O8 2-. Once I pour them in the large beaker, I have to start the chronometer. Once the two reactants react together, I observe a yellow color that darkens with time to be orange, then brown. This is due to the formation of I2. Now, at a specific instant, for example, for t equal 1 minute, I will use a pipette and I will take a specific volume. Here it is 5 milliliter. So this is a 5 milliliter volumetric pipette. I will take 5 milliliter from the mixture here and pour them in the first Erlenmeyer. So the color in the Erlenmeyer will become yellow. And the production of I2 in these 5 milliliter will stop here. It will be blocked. At another instant, for example, t equal 2 minutes, I will repeat the same procedure. So with the same pipette, I will take another 5 milliliter from the mixture here that produces I2 and I will pour them in the next Erlenmeyer. The same procedure is repeated at another instant, which is 4 minutes, and 5 milliliter are taken from the mixture and poured in the Erlenmeyer, and for t equals 6 minutes, the same procedure is done. Pay attention here that the color of the solutions becomes darker when time passes. Even though I have the same volume of water and the same amount of the mixture taken. Since the amount of I2 produced in the 5 milliliter here is smaller than that, here, smaller than here, smaller than here, after being added to cold water. So, when pouring the content of the pipette into very cold water, the concentration of the reactants and the temperature decrease dramatically the rate of this reaction and stop the formation of I2. Now, I2 produced in each Erlenmeyer will be determined by titration, but before we have to use a color indicator, which is starch. So, starch is added to each Erlenmeyer to give a dark blue color. Now, this is our Erlenmeyer that contains I2 and starch. This is the setup of titration. S2O3 2- thiosulfate ions are put in the burette. The equation of the titration reaction is the following. Pay attention. Titration reaction is very fast. It is an instantaneous reaction as you have taken in grade 11. So the decrease in the temperature and in the concentration of reactants won't affect it. And at equivalence, the color in the Erlenmeyer will pass from dark blue to colorless, which is the color of S2O3 2- by 1 drop in excess. It's very important to mention this. To sum up, we have two reactions in this kinetic study. We have the equation of the slow reaction, R1, which is the reaction that produces I2. We have the second fast titration reaction, R2, in which I2 produced from R1 is being titrated by S2O3 2-. The reaction R2 will allow me to determine the number of mole of I2 produced in reaction 1. How? By writing this relation that you know from grade 11. R2 allow me to say that at equivalence, reactants react according to their stoichiometric ratio. So, the number of mole of I2 found initially in the Erlenmeyer or the beaker over 1 is equal to the number of mole of S2O3 2- added from burette over 2. So C1 V1 is equal to C2 V equivalence over 2. By this relation, I can determine the number of mole of I2 produced by the reaction 1 or its concentration. In addition, if I'm asked to determine the number of mole of I- remaining at an instant t in the reaction R1, I have to write the relation that I know. The number of mole of I- remaining at an instant t is equal to the number of mole of I- initial minus the number of mole of I- that has reacted. In the reaction R1, the number of mole of I- reacted over 2 is equal to the number of mole of I2 produced over 1. So instead of n of I- reacted, I can put 2n of I2 formed at T. We have seen this before. Also, in the reaction R2, the I2 produced is equal to n of S2O3 2- over 2. So between R1 and R2, I2 is in common. So n of I- over 2 will be equal to n of S2O3 2- also over 2. By simplifying 2 and 2, I can put instead of n of I- reacted, n of S2O3 2- and I can replace it by C2 V equivalence. As an application for this experiment, please take 15 minutes to solve number 3 of the sheet, then check your answers. Another example of a slow reaction, the decomposition reaction of hydrogen peroxide. Hydrogen peroxide is an antiseptic used to clean cuts and wounds. The decomposition reaction of hydrogen peroxide is the following. Hydrogen peroxide decomposes to produce water and oxygen gas. This reaction is very slow at normal conditions, so that if I pour H2O2 in a beaker, I cannot observe oxygen released during this decomposition. This decomposition reaction can be accelerated by using a catalyst like Fe3+ ions. So if I add few drops of a solution containing Fe3+ ions, I can observe decomposition of H2O2 and the release of O2 gas can be observed. To determine the concentration of H2O2 remaining at different instants, I'm going to perform the following experiment. Let's see. Before performing this experiment, I'm going to prepare my ice water bath in which I will put 4 Erlenmeyers containing the same amount of water between 150 and 250 milliliter. This is the solution of H2O2 to which I have added Fe3+ ions, and I start the chronometer. At t equal 3 minutes, I will use a pipette. I will take a specific volume Here it is 20 milliliter, and I pour them in the first Erlenmeyer. Once I pour them, the decomposition reaction of H2O2 in these 20 milliliter will stop. Again, at T equals 6 minutes, I will take, by using the same pipette, another 20 milliliter, and I pour them here. The decomposition of H2O2 in these 20 milliliter will stop also. The same procedure is repeated for T equal 9 minutes and for T equal 15 minutes. Pay attention that the number of mole of H2O2 in the Erlenmeyer at 3 minutes will be more than that at 6 minutes, more than that at 9 minutes, and more than that at 15 minutes. And the number of mole of H2O2 remaining in each Erlenmeyer will be titrated by using a convenient solution. For the titration of H2O2, the convenient solution is potassium permanganate KMnO4. This is the Erlenmeyer that contains H2O2. It is colorless. This is the titration setup. MnO4 minus is put in the burette. The equation of the titration reaction is the following. Also, the titration reaction is very fast, so it is not affected by the sudden cooling that we have performed previously. We start the titration, and MnO4 minus will be added to the Erlenmeyer, and at equivalence, the color in the Erlenmeyer will pass from colorless to pink or very light violet, which is the color of MnO4 minus, by the excess of 1 drop. To sum up, I have the first slow reaction, and this is the equation of the titration reaction, which is a fast reaction. The number of mole of H2O2 remaining from the reaction R1 will be titrated by MnO4 minus in reaction R2. Reaction R2 will allow me to say that at equivalence, reactant reacts according to their stoichiometric ratio. The number of mole of H2O2 found initially in the Erlenmeyer or the beaker over 5 is equal to N of MnO4 minus added from burette over 2. So the number of mole of H2O2 over 5 is equal to the number of mole of MnO4 minus over 2 equal to C2 V equivalence over 2. So the number of mole of H2O2 remaining at an instant T in reaction R1 is being titrated in reaction R2. So I can put the number of mole of H2O2 at instant T is equal to 5 times C2 V equivalence over 2. As application for our previous experiment, please take 15 minutes to solve number 4 of the sheet, then check your answers. By this video, we came to the end of the part Chemical Kinetics. Assalamu alaikum.